students. Today you have to discuss Ohm's law. Ohm's law, how that Ohm's law is related to the drift velocity. Drift velocity, Ohm's law, how they are related. What the Ohm's law tells, it states that at constant temperature and pressure, the current flowing through the conductor is directly proportional to the potential difference maintained across its conductor, across the two ends of the conductor. Means you know that whenever the potential difference is maintained, then the electric field is set off along the conductor and current is set off, current is produced. And that current V is directly proportional to I and V equal to I into R. You know it. V equal to I R, you know it. So how this R term, resistance term, will be expressed in terms of relaxation time is expressed in terms of the drift velocity. That thing the derivations of Ohm's law. How to derive the Ohm's law? Because you know whenever potential difference is maintained at the two ends of the conductor, electric field is set off. It is clear whenever the conductor is here, when PD is maintained, if you are maintaining the PD, if V1 is here, potential is given V1 and here you are giving the potential V2 and the potential difference is V1 minus V2, the current will be produced along this direction. That is, electric field is set off along the conductor. And the electrons inside the conductor will be drifted opposite to that of the electric field. Opposite to that of the electric field. In this direction, electrons will be drifted. So when PD is applied, electric field is set off and electrons are drifted opposite to that of the electric field. Clearly. So in this case, what you are finding, the electric field whichever is set off, that is E equal to minus V upon L. Because you know that is E equal to minus dB by dL and that is E equal to minus V by L. V is the potential difference, V1 minus V2. That is V equal to here, that is V1 minus V2. That is potential difference maintained at the two ends of the conductor and L is the length of the conductor. Another thing is that the electrons which will be drifted opposite to that of the electric field, the expression for the drift velocity, you know it, the drift velocity expression is minus small e, capital E, relaxation time upon m. That is, E is the charge of the electron, capital E is the electric field intensity, T is the average relaxation time, m is the mass of the electron. That negative sign indicates it is opposite to that of the electric field. And that is equal to, if you put for E, in place of E, you just put minus V by L. If you put the minus V by L, that minus minus becomes plus. So remaining is the E, V, average relaxation time upon ml. You are finding this term, that is the drift velocity. E, V is the potential difference, relaxation time upon mass into length of the conductor. That is the VD, that is the drift velocity of electrons. And another relation, you know it in the previous video, that how the drift velocity is related to the electric current, and that is I equal to NEAVD. You know this formula, that is I equal to NEAVD. Again I am telling the terms. N is the number density, number of electrons per unit volume, number of free electrons per unit volume. E is the charge of the electron, A is the area of cross section of the conductor, and Vd is the drift velocity of the electrons. So simply you are writing NEA and in place of Vd you are putting EV relaxation time upon ml. So EV relaxation time upon ml. And if you are just collecting it here now, N is square A relaxation time upon ml into V, that is the potential difference. Or if you keep the V on one side, that ml will be coming this side. So V equal to I ml upon N is square A into relaxation time. V equal to I ml upon N is square A relaxation time, that is equal to I into R. and we are finding V equal to I into R, and in place of R, what thing you have written? We have written that is the ml upon n e square a into relaxation time. This is the expression for that proportionality constant from the Ohm's law, you know, that is the R. The R proportionality constant is called the resistance. This is called the resistance, and hence the expression for the resistance is resistance of the conductor is, that is ml upon n e square a into relaxation time. Resistance of the conductor, that it opposes the flow of current through the conductor. Resistance which opposes the flow of current through the conductor. So from this term, what you are getting it, because the resistance depends upon the L directly proportional. If the length will be increased, length of the conductor will be increased, the resistance also will be increased. If you think for the N number density, more the number density, resistance will be the less. Where you can get the number density of electrons more, particularly for the conductors, copper, iron, the number density will be more. The number density of free electrons for copper is more than that of the iron. The more number of free electrons means number density is more. So more the number density, resistance will be less. If the resistance is less, means the current obstruction will be less. And that is the area of cross section. If the area of cross section is more, then resistance will be less. For the thicker wire, if the wire will be the thick, then the resistance will be less. And another term is the relaxation time, average relaxation time. The resistance of the conductor also depends upon the average relaxation time, that is inversely proportional. How it is? Suppose if you heat the conductor, the relaxation time will be reduced. The free electrons, they will be colliding each other frequently, and due to that reason the relaxation time will be reduced. If the relaxation time will be reduced, then resistance will be increased. So that it means whenever the metals or conductors will be heated, the relaxation time will be reduced, and the resistance will be increased in this case. This is the expression for the resistance of a conductor in terms of the relaxation time. You just shouldn't mind it, because some numerical you will be finding this type of expression, that is R equal to ml upon n e square a into relaxation time. From Ohm's law, you know it, if you plot the graph in between the V and I, and if you plot the graph between the V and I, that becomes a straight line. V and I, then it becomes a straight line. Suppose you have taken that V is here and I is here, wherever you take it, and the graph becomes like that straight line. The graph becomes a straight line. So that is for the ohmic conductor. For ohmic conductor means the conductor, the metal or the material which follows the Ohm's law are called the ohmic conductor. Ohmic conductor. This is for the ohmic conductor. And in ohmic conductor, the metals and alloys are coming into the ohmic conductor. Metals and alloys are coming into the ohmic conductor. And for non-ohmic conductor, the metals and alloys will be like that. For the that will not be a straight line. That is for the non-ohmic conductor. Non-ohmic conductor, the graph is not a straight line. If you can take it the I and I versus V also, no problem. Then the graph becomes graph is not a straight line for the non-ohmic conductor, the conductor which doesn't obey Ohm's law. So that is coming into the category of gases, coming into category of semiconductors. These are the non-ohmic conductors. So the graph between the VI graph or IV graph, that is the for the ohmic conductor, and it is for the non-ohmic conductor. And this is all about your Ohm's law. In the next video, we will discuss more about the resistance and resistivity. Thank you.